Welcome to The Explainer. So today, we are unpacking a truly transformative piece of educational material, how to think like a computer scientist learning with Python. If you've ever wanted to learn to code but just felt, completely overwhelmed by all the jargon, the complicated setup, or the sheer mathematical abstraction of it all, take a deep breath. You're in exactly the right place. Okay, let's dive into this and demystify programming once and for all. As you'll see, learning to code isn't really about fighting with a computer. It's actually about learning a completely new way to think. Educator David Beasley really hits the nail on the head here. He perfectly captures why so many of us have tried and failed to learn to code in the past. Traditional computer science education often just throws you straight into the deep end of mathematical abstraction and this rigid, totally unforgiving syntax. You end up spending, half your time trying to sort out completely unintelligible error messages instead of actually solving the problem you set out to solve. It's incredibly frustrating. And hey, if you've experienced that, your struggles are entirely valid. Section 1, the programming language problem. So to really get why this happens, we have to look at the tools educators were forced to use back in the day. Back in the late 90s, high school teachers like Jeff Elkner, who actually helped adopt the book we're exploring today, were tasked with teaching advanced placement computer science using C++. And Elkner found himself just constantly fighting with C++'s difficult syntax. It was this massive hurdle, and he was losing students left and right unnecessarily simply because the language itself was getting in the way of the core concepts. I mean, just look at this historical hurdle. In C++, writing a basic Hello World program requires you to understand things like include, void main, and just a whole mess of brackets, all just to print a simple message. It's super intimidating. It basically forces a teacher to say, yeah, just ignore all that weird stuff for now. But with Python, you literally just write print Hello World. That's it. It is beautiful in its simplicity. Python allows you to essentially just do it in English. You type what you want to happen, and it happens. There's no arcane boilerplate code standing between you and your first successful program. And because Python lets you just do it in English, the impact on learning is absolutely profound. Elkner notes that when he compared the C++ version of his textbook to the Python version, whole paragraphs of explanation just vanished. Why? Well, because those paragraphs weren't actually teaching computer science. They were just explaining the agonizing minutia of C++ syntax. By using a high-level, highly readable language, you get to completely skip the low-level machine details. You get to put the big ideas first and actually focus on the concepts of programming, rather than, constantly fighting the computer's architecture. Section 2, thinking like a scientist. Okay, so if we take away the friction of the language, what is it that we're actually trying to learn? That brings us to the core philosophy of this text. Learning to program isn't just about memorizing a list of commands. It's fundamentally about learning a completely new way to process the world around you. It turns out this new computer scientist mindset is actually a really unique hybrid of three distinct disciplines. Just like mathematicians, computer scientists use formal languages to denote complex ideas. Like engineers, they design things, assembling components into systems, and constantly evaluating the trade-offs between different approaches. And, much like natural scientists, they observe the behavior of complex systems, form hypotheses, and test predictions when things don't work exactly as expected. Because at the end of the day, the single most important skill a computer scientist possesses isn't typing fast or knowing every single Python keyword by heart, it's problem solving. It is the ability to formulate a problem, think creatively about how to solve it, and then express that solution clearly and accurately. Writing the actual code? That's just the final step. It's really just a means to an end. The real work happens in your head way before your fingers ever even touch the keyboard. Moving into Section 3, formal versus natural languages. Once we've got that brilliant solution in our heads, we do still have to express it to the computer. And this is where we really have to understand the difference between the language we speak every day and the language the computer reads. We are all super used to natural languages, right? Things like English or Spanish. They evolved naturally over thousands of years, and honestly, they're incredibly forgiving. In English, you could spell something wrong or use terrible grammar, and I can still usually guess exactly what you mean just from the context. But formal languages, like mathematics or Python, they are an entirely different beast. They were meticulously designed by people for specific applications, and they have strict, totally unbending rules. So while Python lets you essentially do it in English by using highly readable words, make no mistake, it is still a formal language. It is completely literal. There's zero ambiguity, and the computer simply cannot guess your intentions. And because of this extreme, literal nature, you actually have to train yourself to read code differently than you'd read a novel. You can't just casually skim it left to right, top to bottom. You really need to parse the program in your head. You have to identify the individual tokens, the basic elements of the structure, and carefully interpret how they all fit together.
Even though you're doing it in English with familiar words like print or if, the details, the spelling, and the punctuation, they matter immensely. I mean, a single missing quotation mark is literally the difference between a perfectly working program and a computer throwing an absolute tantrum.
All right, Section 4, the building blocks of code. Once you actually understand how to read a formal language, you can start using its basic elements. And the truly amazing thing about programming is that every single piece of software you have ever used is made up of just a few foundational concepts. Let's look at a couple of them. The first major building block we need to talk about is the variable. And hey, don't worry, it's way less intimidating than it sounds. In older, lower-level languages, a variable is strictly tied to the hardware. It's a specific size of a specific physical place in the computer's memory. But Python takes this much more intuitive human approach. In Python, a variable is simply a name that refers to a value. It's incredibly straightforward. You just say, message equals, what's up, doc? You are simply naming a thing, exactly like you would in everyday English. This is huge because it allows you to completely ignore bytes and memory addresses and just focus comfortably on the actual logic of your problem. Then there's this another massive leap in readability when you get to functions. The absolute beauty of Python's def keyword is that when you want to define a new function, which by the way is just a sequence of statements that performs a specific operation, you literally just write def, followed by the name you want to give it. This lets you hide really complex computations right behind a single descriptive English word of your choosing. You encapsulate all that complexity, making your main program smaller, way easier to read, and honestly, just much easier to think about. Now, as you start mixing these variables and functions together, your programs are going to get bigger. And this is exactly where beginners tend to get stuck. They write like 50 lines of code, run the whole shebang, it breaks, and they have absolutely no idea where the problem is. The solution here is incremental development. Think of it kind of like building a house. You start with a tiny foundation that you know works. You make a small change, like, I don't know, adding one wall. You test it. If the wall falls over, you know exactly which wall caused the error. You use temporary variables to check your math along the way, acting as sort of scaffolding. And once that section works perfectly, you can just remove the scaffolding. It is a highly structured, totally stress-free way to build really complex things. Which brings us to Section 5, the art of debugging. But even with incremental development, because humans are the ones writing the code, errors are just inevitable. And in programming, we affectionately call these errors bugs, and the process of hunting them down is debugging. To actually troubleshoot effectively, you need a solid mental framework that breaks down the 3 distinct types of errors you're going to face. First up, syntax errors. This is when you break the strict rules of the formal language, like, say, forgetting a parentheses. Python catches these immediately and flat out refuses to run. Second, we have runtime errors. Here, the syntax is fine, the program starts, but something literally impossible happens during execution, like trying to divide by 0. And finally, semantic errors. This is where the program compiles, it runs perfectly without crashing, but it gives you the entirely wrong answer. Now, semantic errors, those are definitely the trickiest. Because as far as the computer is concerned, everything is perfectly fine. The flaw is strictly in your logic. When you face a semantic error, you really have to ask yourself a few practical questions. Is a step missing? Actually, wait, is it doing something extra that it shouldn't be? Is the math evaluating in the wrong order because of some missing parentheses? And most importantly, and we've all been guilty of this, have you actually read the documentation for the tools you're using? Debugging isn't just mindlessly fixing typos. It's a very active, scientific process of forming hypotheses about what's wrong and then systematically testing them. Section 6, a collaborative mindset. Let's kind of zoom out for a quick second here. We've talked a lot about the solitary act of reading and writing code today. But one of the most beautiful takeaways from this source material is that code and the education around it is very rarely built in isolation. The actual origin story of this textbook proves that perfectly. It literally started out as a Java textbook by Alan Downey. Then Jeff Elkner found it, and because it was released under a free license, he translated it into Python to help his high school students. After that, a professional programmer named Chris Myers jumped in to help write the more advanced chapters. And finally, the students themselves perfected it, earning bonus points for catching typos. It just goes to show that programming isn't this isolated, lonely struggle. It's a collaborative, open-source community effort. When you learn to code, you are joining a massive, global community of problem solvers. So, what can you actually do with the support of that community and those basic building blocks we've discussed? Well, the source text introduces this genuinely mind blowing concept called the Turing thesis. It essentially states that with just the basic subset of features you learn in the very first few chapters of Python, variables, simple math, if statements, and loops, you can theoretically compute absolutely anything that is possible to compute. You do not need 1,000 complex commands. With just a few simple tools expressing your logic in straightforward English-like syntax, the possibilities are quite literally infinite. And that brings us to our final thought. The barriers to entry, they're completely gone. You don't have to fight arcane syntax anymore. You can just do it in English. You have the framework to build things incrementally, and you've got the mindset to debug problems like a true scientist. So now that you have the mental toolkit to actually think like a computer scientist, what problem are you going to solve first? Think about it. Thanks so much for joining me on this explainer, and hey, happy coding.